All right, number 1 from section 4.6 says assume that the matrix A is row equivalent to B. Why does it say? Okay. And it says, without calculations, list the rank of A and the dimension of the null space of A. So first, let's find the rank of A. And remember, we've mentioned this before, the rank is the dimension of the column space of the matrix. So there's nothing new here. If it's in echelon form, you just have to count the number of pivot columns. 1, 2, 3. There are 3 pivot columns. That means the rank of A is 3. All right, easy. Next part is the dimension of the null space of A. Well, you just have to use that equation that says the dimension of the column space of A, which is the same thing as the rank, plus the dimension of the null space of A is equal to n. And we always assume that our linear transformation takes vectors in Rn to Rm. So really, what is n? It's just the column matrix that you'd have to multiply A by to go into some other space. And the only way that this product would be defined is if the number of elements is 5. It's really just the number of columns of A is what n is, and I've mentioned that before. So n is equal to 5, and we already know the rank is 3, and really I don't need to say the dimension of the rank. The rank is just a number. So 3 plus the dimension of the null space is equal to 5. That means x has got to be 2. So the dimension of the null space of A is 2, just using that equation. All right, those are the first 2 parts. Now part C is find a basis for the column space of A. Okay. And we've done that before already too. There is one thing in this problem we haven't done before, and we'll get to it in a second. But this is just more review. A basis for the column space of A. Well, remember if 1, 3, and 5 are the pivot columns of the echelon form, then you can use 1, 3, and 5 as your basis elements for the column space in the original matrix. So we could use that as our basis. Done that several times already. All right. And now let me enter that. All right, now that's the basis for the column space. Now what about the row space of A? They want us to come up with the basis, or a basis, for the row space of A, okay? Now this is something we have not done yet. This is something that's a little bit new. But let me just give you the fact. If you take a matrix and you put it in echelon form, you can come up with a basis for the row space just by using all of the non-zero rows in the echelon form of the matrix. So I can just say this is a basis element, this is a basis element, and so is this. You just take the non-zero rows of the matrix in echelon form, and that'll give you a basis for the row space. It's as simple as that. So I can use that as my basis. So one of them is this. So that's kind of a nice fact. And remember, the row space is essentially just all the linear combinations of the rows, if you think of them as 5 by 1 vectors. All right, so x1 times this, plus x2 times this, plus x3 times this. That'll span the space, the row space. So kind of easy. I think there is one more part to this. But we also want a basis for the null space of A. And that also is just review. So really the only new thing in this problem was part D. But let's see if we can come up with a basis for the null space of A. Now remember, that's just the a basis for the space that you get if you consider all the vectors that will satisfy this equation for x. Okay, so essentially I just need to just take my matrix A, come up with a system of equations by making that last column a column of zeros. And then we'll see what the solution set is. And in fact, if I do that, row operations will take me right down to echelon form anyway, so I could probably skip that and just go right to echelon form. But we want to put this thing in reduced echelon form because we want to characterize the entire null space. So we sometimes want to go a little bit further and put it in reduced echelon form. But not much to do here. It looks like if I just take the second row and multiply it by -3 and add it to the first row, I can make that a 0. So -3 times that plus that. -3 times that would be 3, minus 1 is 2. -3 times that would be 9, plus 3 is 12. Okay. Almost done. Now we've got to make these two guys zeros. I think I might be able to do that in one step. I think this is easier than or faster than using a calculator. Sometimes it is. 3 times this plus that. And then -12 times this plus this. That'll make that a 0. But it won't change the other elements. All right. And we've done this trick before, but it's a good review. So the only thing that was really different was that row space idea. But let's see, this first equation, if I solve for x1, that's what I get. Looks like the two free variables are x2 and x4. Okay, this equation would be x3 equals x4. This one just says 1, 2, 3, 4, 5. x5 is equal to 0. All right. So let's do the usual trick. Every vector in the null space will look like that, but we can put it in terms of just two variables, it looks like. x3 is equal to x4, x4 is equal to x4, and x5 is equal to 0. All right, so there's your basis. There's your, right there. And you can check for linear independence, but I'm sure they're linearly independent. That's for the null space.